expensive. It's too expensive. It's too expensive. It's too expensive. This is Cousin Dan. Last time I was on the Baseball Hippy show, the Baseball Hippy asked me in the hardball question, what is time? And that threw me for a loop because I think about time a lot because I have gotten pretty into learning about
relativity ever since that black hole gravitational wave thing, and I've just been interested in astrophysics, and I watch a lot of videos and read a lot about it.
There are these things called photons, and they are light particles. So like light, when it comes from the lamp in your room or anything that has visibly glows bright, or the sun.
In the 19th century, there were all these experiments that determined that no matter where you were or how fast you were traveling, the speed of light was always the same. Photons, you would always measure photons as traveling at the same speed.
The photon clock is a thought experiment that Albert Einstein came up with to describe special relativity, or explain what was happening. So this is the photon clock. The red dot that's traveling is the photon, and one tick of this clock is the time it takes to travel along the square. So up is a tick, and then back down is another tick. So here we see this one inside of baseball for the Baseball Hippy show, going on 5 ticks. All right, so now I'm going to show the next photon clock sort of experiment here and show what happens when a photon clock is traveling relatively close to the speed of light. So, all right, so here we have the photon clock, and now let's look what happens while it's in motion here. Okay, so now the photon clock inside the baseball is traveling relatively close to the speed that the photon is traveling inside. Now, remember that the fact that we're using for this thought experiment is that a photon, no matter where you are, you will observe it traveling at the same speed. So the photon is traveling inside the clock up, but it's inside the baseball, which is traveling relatively close to the speed of light. So what we see happens is that it's moving in the horizontal direction while it's moving in the vertical direction. And so we get that old Pythagorean theorem hypotenuse thing, where this is actually how far it's gone in the time it would take to move in a stationary photon clock. So now we'll go on to the third, putting both of these things together, and then we'll look at what happens when there is a photon clock that is stationary and one that's moving. All right, so now we've got one photon clock up here, which is going to remain stationary, one that's going to be hit by some epic Ichiro in a near light speed line drive. And we got the view from Roger Schmotis out in, outside of right field here. And he's going to and we're going to see what happens. Now, we're going to trace the path of the moving photon in total here. So as this baseball moves near the speed of light, the photon is moving inside of it. Meanwhile, we can see this one up here is already on its 7th tick, and we just hit the 3rd tick in the moving baseball. And so what's happening is that if you had someone inside that baseball photon clock and they were observing this, they would say oh, hey, look, 5 ticks have passed. And to them, it would feel like they'd just been inside of there for 5 ticks of this clock. But to someone who is observing from far away, that person and that clock inside the moving baseball has moved slower than the stationary clock, which has ticked 15 times in the time that it took this moving clock to move the 5 times. And that's because the outside observer is seeing the diagonal path of the photon as it goes along this crazy sort of diagonal path, and the speed it can go along there is only the speed of light. So if that photon were moving at the same rate, it would actually be moving along that path faster than the speed of light, which would violate all those experiments that that they had done back in the 1800s. I want to go on and talk a little bit about general relativity, which is an expansion of Einstein's theory of special relativity that takes into account gravity. So here we have a bird's eye view of a baseball diamond. Now you have in here in the infield, you got the runners, you got the baseman, the pitcher, and the shortstop. And so you have the 5, and the catcher. So you have 6, 6 people fielding, and then you have some number of runners.
Not nine people in the field.
Yeah. So
3
then you got
outfield.
and then you got the 3 people in the outfield. Now, what this got me thinking was that means that to be a fielder, you have to be a better runner, right? Because the ball is going to come to you anywhere, in some area in your zone, so that got me thinking that's kind of like how gravity works in general relativity. You have more players here, so the gravity is stronger in the infield. So the way that the players, if you kind of think of them as particles, move around, they move a little bit slower relative to the running over the distances that the outfielders have to do, because they're in this big empty space where there's less particles and less gravity. I don't know. Maybe I don't know a super lot about general relativity, and I don't know a super lot about baseball. So that's maybe not the best metaphor in the world, and it certainly will not extend farther to give you kind of ideas about how other things work. But I think I kind of like it because it gives you an idea of the effect that when you're in a high gravity place, time moves a little bit slower. So satellites that have been in space orbiting the Earth in the lower gravity of orbit, they actually, the computers will lose a little bit of time after it's to the point where they lose 1 millisecond after being in space for 20 years or something like that. So it's very slow how this happens. The effects are much more pronounced closer to big objects like stars, black holes, etc. But still, that's the way that this sort of special relativity kind of extends. Einstein's whole theory of relativity is all about how time is perceived differently depending upon what speed that you're traveling at, or how close you are to massive gravitational objects. So time does not move the same at all places in the universe or at all speeds. So time is, in some ways, a subjective thing, and it's defined by the causality, by the process of events that's happening around where we are. So that is my really, really long, overly complex answer to your hardball question of what is time.